Hey everyone, and welcome back to our electronics tutorial series. My name is Aaron from AX Electronic, and today we're going to continue on the topic of BJTs, and I'm going to show you how to simulate them using LTSpice. So if you're not familiar with LTSpice, it's a very powerful free tool that allows you to simulate circuits, probe around, maybe see all the voltages and all the currents. That way you can really get an intuitive feel without having to actually build the circuit. Plus, it's a great design tool. It's a great step before you actually build a circuit to make sure it's going to work out before you spend money on components and things like that. And knowing how to simulate these BJTs and LTSpice is really going to allow you to explore the world of circuits and especially explore the next circuits that we're going to be looking at in the coming videos. So let's go ahead and get started. So I've already got my LTSpice window up and running. And the first thing that I want to do is that I'm going to go ahead and add in a BJT. So I'm going to press F2 to bring up the component window. Now, if we wanted to add a MOSFET, we had to either add an N channel or a P channel. So in LTSpice, that's NMOS or PMOS. For this, we're not doing NMOS. We're going to do NPN. Okay, NPN, because that's the type of transistor that we want to add. And I'm going to go ahead and do a little bit of housekeeping and just go ahead and put a ground there and connect it up. So we have our emitter connected directly to ground. So what we're going to do is that we're going to try and look at how this transistor operates whenever we feed it a variety of different currents, okay? So what I'm going to do at first is that I'm going to add a voltage source at this collector because we need a voltage between the collector and emitter in order to allow current to flow. So I'm going to press F2, type volt, and bring up a voltage source. Connect one side to ground and connect the other side to the collector. Now, I'm just going to keep this simple. I'm going to keep it at 10 volts. And boom, we've got our collector wired up. Now, whenever we were probing around for MOSFET curves in our previous LTSpice video with MOSFETs, what we did is that we had a voltage source on the MOSFET gate, and we would sweep that voltage source to see how the current would change. Now, that is because a MOSFET is a voltage-controlled current source. BJTs are a current-controlled current source, meaning that we have to feed in an input current to its base and not a voltage. So just to give you an example, if I did add a voltage source here, and let's say I swept it to, oops, let me make sure I move that to the right spot. Let's say I swept this voltage source all the way from 0 to 10 volts or something like that. Well, remember, we have a diode in this transistor that's going to start conducting at about 0.7 volts. So as soon as we start adding some current, or as soon as we start reaching a voltage above that diode drop, we're going to start conducting a lot of current very quickly. And that can be very bad for our diode because that is going to cause it to conduct a lot of current, get very hot, and probably damage the device. So instead of adding a voltage source, I'm going to add a current source. So to add a voltage source, we would use voltage. For a current source, we're going to use current. I'm going to select the current source. We're going to make sure that we're feeding current into the base of this transistor because current has to go into the base. So I'm going to press Control R 2 times to rotate it. Go ahead and connect it to that ground slot. I'm going to select my grab tool, so I'm going to press F8. I'm going to grab those and just bring them down a little bit so I can have a good amount of space to wire everything up. Oopsies. Get rid of that so it looks nice. All right. And I'm going to go ahead and give this a default value of, let's just say, 1 milliamp. Now, what we are trying to do is that we are trying to simulate the curves for a specific transistor. Now, this one here is LTSpice's version of an ideal transistor, but it's not going to behave the way that we actually want it to or that we're actually expecting it to. So we need to pick a new one. So I'm going to right-click on this symbol and click Pick New Transistor. And we're going to use the first one, the 2N2222, because it's a very, very common NPN transistor. Now, we have got everything set up the way that we want it to, so let's go ahead and try and simulate. So I'm going to come up to the top and press Run. Now, we're not going to do a transient analysis. What we're going to do is we're going to do a DC sweep. So we've done DC sweeps with voltage sources before, but you can actually do them with current sources too. So we first need to tell it the name of the source to sweep, and that is I1. That's what we want to sweep. We're going to do a linear sweep. We're going to start at 0, and we're going to stop at, let's just go 100 milliamps in the very, very beginning, okay? So let's go 100 milliamps. That's a nice broad range, and maybe we'll look at some lower current cases here in a moment. And we'll do let's do a 0.1 milliamp step. If we press OK, we're going to get our simulation up and running. I'm going to go ahead and move this around. That way it's a little bit better looking. Click here. All right. So Now we can start probing around and seeing all these different curves. So first, let's check out the base current. So the current that's going into the base, we're expecting this to be linear because this is the voltage that we're sweeping, so we want it to be a linear increase. We have our 10 volts on our collector, our emitters tied to ground. Let's check our voltage at the base. So what we can see is that whenever we just start conducting, maybe around 1 milliamp or so, we have about that 0.7 volt diode drop that we're expecting on that transistor. But as we start conducting more and more, this is not going to behave as much like an ideal diode, so it's going to start increasing its voltage drop very, very quickly. So by the time we're pushing 100 milliamps through this transistor, we're actually all the way up to about 2.4 volts. So if you are going to be driving a very high current source, then you're going to be needing to know this and take it into account whenever you're doing your calculations. But if it's more of a low current, technology, then what we can do is that we can just approximate it as that 0.7 initially. And then if you do need that additional accuracy, you can simulate or test in order to get what it would actually be. Now, that is our base voltage. Let's check our collector current. So this is our collector current versus our base current. Now what we can see is that, again, for this low area here, we're getting a pretty high slope. So if we just look at this one area, we have a pretty high slope. And as we drive this transistor hotter, that slope is actually decreasing. Okay, so here this slope is not as high as it was previously. So it looks like it's kind of tapering off as it reaches the top. Okay, and what we can see is that this is actually how we're going to calculate beta. And if you look on a very good data sheet, they'll actually have beta at a bunch of different points. So they might have beta at 10 milliamps. So they might calculate the slope here. They might also have one over at 100 milliamps where they're going to calculate that slope. That way you can kind of get an understanding of maybe how this parameter changes as we are supplying different currents and voltages and things like that. So that is our collector current. Let's try and modify this a little bit because we're seeing a lot of behavior that maybe we're not expecting too much. And the reason for that is because we are sweeping this to be a very, very high base current. Now, if you have 100 milliamps and you have a beta of like 50, that's going to be driving 5 amps on the output. Now, we haven't quite gotten there with this one. We're driving about 2.4 amps, but this is still a whole lot of current. It's a very high current application. So let us go ahead and drop it down to maybe just 10 milliamps in the beginning. We'll drop down this step too to be a little bit smaller, like 1 microamp. And now let's see what's happening here. So now this is starting to look a little bit more linear. It still has that kind of taper off, so maybe we'll do a little bit closer simulation here in a moment. Let's check our voltage. So our base voltage, we can see that now it's a whole lot closer to this 0.7 volts that we are used to and that we're designing for. So at 10 milliamps, we're up to about 1.08, 1.1 volts. Okay, so that's still a little bit closer than it was previously. Maybe we can drop this down again. So let's just drop it all the way down to 1 and do another simulation. Okay, so now our voltage is right about at that 0.7 volts. So we're not straying too far away from that 0.7 volts. And this is a little bit more of a realistic case. So let's take a look at our collector current to see what we have here. So if we only have 0.1 milliamps into our base, what we have is we have 20 milliamps on the output. So here, that is actually corresponding to a beta of about 200. So what you can see is that whenever we're actually driving it with lower current, we have a beta that's a whole lot higher. And then the higher current we get, or the higher collector current that we have, we're actually going to be decreasing that beta. So that's going to kind of be a trade-off, okay? So that's something you have to take into account, that beta is going to change depending on where your operation point is. But usually whenever you're in the low current area, which is kind of what you want, we're going to have a pretty nice beta. So this looks almost linear. We can still tell it's not exactly linear, but it looks a whole lot better than it did previously. So what I encourage you guys to do is that I encourage you to kind of play around with this simulation, make it for yourself, and maybe see how changing this voltage or how changing that collector voltage impacts this current. Is our current always the same no matter what base volt or no matter what collector voltage we have, or does it maybe change at one extremity or the other? So I encourage you to do that to really get a feel for maybe these different operation regions where we want our transistor to be operating at, okay? Now, if you guys have any questions, please feel free to leave them in the comments section below. If you enjoy this content, please give me a thumbs up and subscribe to see more. It does keep me extremely motivated to see new likes and new subscribers. Other than that, thank you guys for watching, and I will see you next time.